So today I'll be taking this lecture, and so today I'll be giving a quick recap about controllability, reachability and stabilizability, which was discussed in the last lecture. And then I'll be solving one problem which was also discussed in the last lecture, which was this stir tank heater. And then I would be so there will be one more example which will be solved, and then I will be introducing the concept of observability and detectability. So it's kind of a dual concept: controllability, stabilizability, and observability and detectability, kinds of dual concepts. So one takes care about those controllable aspects of the controller. The other is something which is important for estimation. So first I would recap about the controllability and reachability. So when I say about controllability, so when there is a system and you have a set of inputs for the system. So when you want to move the system from an initial state to some arbitrary state, say xf, then it is reachability. So you have some initial state x naught, which is not necessarily origin, and then you want to take your system to some final state xf in fixed time instance k. Then this concept is known as the reachability concept. And then when you want to move the system from some initial state x naught to the origin in fixed time instance k, then it is the controllability. Then you can say that the system is controllable. And stabilizability is, so you start a system at some initial state, and then you are trying to stabilize the system to origin at infinite time steps. Then this is known as the stabilizability. So now we need to check whether the system is controllable or reachable or stabilizable. So if you could recall in the last class, Niket would have discussed about the hottest condition, the controllability matrix, the Gramian, and then the use of SVD. So how to separate your reachable states and the non-reachable states. So I will be just saying a few things about those concepts. The first thing is your hottest condition. The hottest condition says, so when the rank of the matrix A minus lambda I B is equal to n, then the system is reachable. And when the rank of the matrix A minus lambda I B equal to n, and if when lambda I is greater than or equal to 1, then the system is stabilizable. The importance of the eigenvalue here, so what it means is, so when lambda is greater than or equal to 1, that means the system is, any autonomous system will be unstable. So when you have a set of input moves which could bring the unstable system to a stable steady state, so that is explained by the stabilizability. So this is generally checked only for lambdas greater than 1, because the lambda is for an autonomous system, and the lambda is greater than or equal to 1, the system is unstable. And to check the controllability, so we have the controllability matrix C, which is power n minus 1 b, power n minus 2 b, etc., etc. The row rank must be equal to n. So in the previous lecture he must have derived how you get this matrix. So basically you start from x of k plus 1. So, I will do it here. So, you start from x of k plus 1 is equal to ax k plus bu k. Then x of k plus 2 is a of x of k plus 1 plus b of u of k plus 1, and then recursively we can say x of k plus ab u of k plus so when you recursively derive, so you are starting, so here x of k will be x of 0. So when you recursively derive it, so when you want to move the system from some initial condition, so it will be a square etc. to a x of 0 plus power n minus 1 b a power n minus 2 b to b a power n minus 1 b a power n minus 2 b, and then you have the set of inputs. So here we are saying that this k. So here we are saying that we are going to move the system from some arbitrary initial state to origin. So when your right hand side, so your left hand side is of the form y is equal to ax. So it is a linear set of linear equations. So to solve this, you need to have, sorry, this is the controllability matrix. So for this equation to have a unique solution x, so this C matrix has to have the rank n. So this controllative matrix must have a row rank of n. So if this satisfies, the system is controllable. So in the previous class he has given an example about stir tank heater. So let us see that example again. So you have your two states, x of k plus 1, x1 of k plus 1, x2 of k plus 1, and you have your alpha 1, alpha 2, 0, b, x1 of k, x2 of k plus. So x1 of, so here x1 of k is the height, and then x2 of k is your temperature. So basically we are saying, so and yeah, u of k is the heater load, say q. So when you are increasing your heater load, so from this equation you can clearly see that doesn't affect the height, and then it actually affects the temperature, because x2 of k plus 1 is alpha 2 of x1 of k plus beta of x2 of k, and then your uk, when you increase the heater load, the temperature will increase. So it is directly related. So can you control your, so how to check for the controllability? Can you control your height h with just increasing or decreasing your heater load? So intuitively we can say that yeah, it cannot be controlled, but how to check for a complex system? So you cannot say directly whether it can be controlled or not. So for that we need to check the controllability, and then first we will check for the reachability concept, which is the hottest condition. The hottest condition says a minus lambda I. So a is 0 1, say alpha 1 0, alpha 2 beta, minus lambda into I 0 0 I, and b is 0 1. So we have to find lambda. So lambda is alpha 1 and beta. So when lambda is equal to alpha 1, we can see the matrix would become 0 0 alpha 2 and beta minus alpha 1 0 1. So, clearly the rank of this matrix is equal to 1. So, for lambda is equal to minus alpha 1, your system is not reachable. So, first we will check and then we will check for lambda is equal to beta. So, when you find the hottest condition for that, so is alpha 1 minus beta 0 alpha 2 0 0 1. So, the rank of this matrix is equal to 2. So, that means one state is reachable, the other state is not reachable. So, how to find which state is reachable and which state is not reachable? So, for that we use the SVD condition. So, we find the SVD of the controllability matrix, which is A, B and B, alpha 1 0 alpha 2 beta 2 0 1 equal to alpha 1 beta, sorry, this will be 0 beta and 0 1. So, this will be your controllability matrix WC. So, when you find the SVD of this, you will get WC transpose. So, we have to find the SVD of this WC transpose, which will be 0 beta 0 1 and 0 0 beta 1, which is equal to 0 0 0 beta square plus 1. So, when you find the eigenvectors, it will be equal to so 0 0 So, this will be U, this will be V transpose, this will be your yeah. So, the transformation which you make, so x of, so we need to find the states which are reachable and the states which are not reachable. So, the transformation which you make here will be so I'll name it as Z1 k plus 1 Z2 of where x is H1 sorry H and T. So, that the transformation T which you have here is your U. So, when you make this transformation, so basically you will be getting T x k plus 1 is equal to A T x k sorry k plus B U k, which is equal to Z of k plus 1 is equal to T inverse A T Z of k plus B U of k. So, when you make this transformation with respect to this A matrix, you can clearly define what is the reachable space and what is your non-reachable space. This concept is very important when you actually consider a complex system where you will have more than say 3 or 4 states, and then say you have multiple inputs. How can you be sure that the input which you make in a complex system would actually affect the particular state? So this is an easy way to actually compute whether your system is reachable or not. And one more important thing is, so when you are actually controlling a system with respect to constraints, so there will be certain case where you will be putting your constraints in the input. So in those cases there will be difficulties where because of the constraints your state won't be reached in a particular, so you cannot reach a particular system state because there is constraint in the input. Say let us assume that your heater load is say 100 kilojoules per minute, and then suppose if you want to reach a temperature of say 400 or 450 Kelvin, since there is a restriction in the maximum heat duty which is 100 kilojoules per minute. So let us assume that the system will reach only say 350 Kelvin, and suppose if you want to reach a temperature of say 400 Kelvin, so that is actually not possible. So this concept of controllability and reachability is applicable for an unconstrained case. So we look into the another example, which is x of k plus 1 x of k. So this will be your A matrix and this will be your mean matrix. So how will you compute your controllability matrix for this? So you want to try? So I'll give you 2 minutes, just try. If you have any queries, you can ask me. So when you just see the system, you can clearly say that the system is controllable. So is the system reachable? So check for that also. So is the system controllable? So when you see the system, at first it appeared to be controllable, at least for me, but when you compute the controllability matrix, so it became you get a matrix with a rank 1 which is less than 2. So you have a 2 cross 2 system and you need to get a rank of 2, and you ended up getting a rank of 1. So the system is clearly not controllable. So we need to check whether the system is reachable or not. So what is the condition for checking for the reachability? So we invoke the hottest condition. We check the rank for A minus lambda I into B. So here we have lambdas is equal to, so it's 2 and 1. So we need to check the hottest condition for the 2 lambdas, which is 2 and 1. The hottest matrix would be 0, 0. For lambda is equal to 2, 1, 0. Okay, so this is the hottest matrix for different eigenvalues. So what is the rank of the first condition for the first lambda? So it's 2. So it is equal to the order of the system, which is 2. So that means there are 2 states here. So you have x1 and x2. You have your lambda for one of the state and you have the lambda for the other state. So it seems that one of the state is reachable, the other state is not reachable. Okay. So, now we need to find which state is reachable and which state is not reachable. For that we are going to use your SVD condition. So, here the rank is 1, so this is reachable and this is not reachable. So, to separate the reachable from the non-reachable states, we use the SVD condition and then come up with a linear transformation. So, SVD of your controllability matrix multiplied by its transpose. So, you want to try this SVD, I will try that parallelly and let us see. So, I think it is 2 2 2 1. So, this is 5 each 5 5 5 5. So, we need to find your lambdas for this. So, lambda is lambdas minus 5 the whole square minus 25, which is lambda equal to 0 and lambda is equal to 10. So, the singular values would be the root of this. So, you will be getting 0 and root of 10 are the singular values. So, then we have to find your U and the V matrix. Okay. So, U matrix is the eigenvector of this. You want to try that again? So, so, this root 10 is your singular value. So, why we are finding why we are using SVD? Because if we do a linear transformation of x is equal to t z, where t is u, we can separate the reachable and the non-reachable states. So, that is why we are doing an SVD. So, if you calculate, you will get u is equal to 1 by root 2, 1 by root 2 minus 1 by root 2, 1 by root 2. Note that u, v are orthogonal matrices. So, when you substitute this u in this transformation, you will be able to segregate your reachable and non-reachable states. So, first we started from controllability. So, we checked whether the system is controllable or not. So, for the controllability we need to construct the controllability matrix and then we need to find what is the rank of the controllability matrix, and once your rank is equal to the order of the system, and then that means your system is controllable. So, what do you mean by controllability? You start from an arbitrary initial state and you want to move your system from an arbitrary initial state to origin, right, at finite time steps. So, that is controllability. And when you want to move your system from an arbitrary initial state to any other state, then it is reachability. So, these two concepts you are doing it in finite time steps. And what is stabilizability? Stabilizability is you have an unstable mode, basically your lambda is greater than or equal to 1. You have a very unstable state, and if you think that you have an input which can push your unstable state to a stable state to origin. So, that is stabilizability. So, if you could do it in infinite time steps, if you could achieve that in infinite time steps, that is stabilizability. So, stabilizability condition is you do the similar Hotter's, you check the Hotter's condition for lambda greater than or equal to 0, because we are concerned only about your unstable nodes, lambda greater than or equal to 1, right. So, for lambda greater than or equal to 1, you check your Hotter's condition, and if your Hotter's condition turns out to be the rank of the Hotter's matrix turns out to be equal to n, that means the system is stabilizable. So, these are the three concepts.